simple linear regression. Let's go over some of the basics of regression. So regression is a statistical method which allows us to use information embedded in one variable to explain the behavior of another variable. The variable used for extracting information is called independent variable. The variable which is explained by the independent variable x is called dependent variable y. If we assume that there is no intelligence available in the absence of any information available from x, the best estimate of the dependent variable y is the expected value e of y. It can also be written as y bar. So it is important for us to understand that y bar forms the base case for comparison with the modeling that we do. So how much gain or how much advantage did we get by including the information from x tells us the value of modeling. For the regression modeling, we restrict, for the simple linear regression modeling, we restrict our functional form to linear form. Hence, we call it as linear regression. Why do we call it a simple linear regression? Because there is only one explanatory variable to explain the dependent variable y. Now we are going to use the information embedded in this independent variable x to get the estimate of y. The estimate of y can also be written as y hat or the expected value of y conditional on x. So both these notations are very common, and the functional form is written as y hat is equal to beta naught plus beta 1 x. So this is a basic premise. We have two variables x and y, and we are using the intelligence or the information embedded in x to explain the behavior or the value of y, and we are restricting our functional form of this relationship to a linear form. Let's get into the specific details of it. We will start with the association of x and y first, and then we will go for the explanation of y using x. So we can perform the test of association between x and y to determine the degree of association or the strength of association. We start with the formula for variance v of x, which is the difference with the expected value of x squared and averaged. So v of x is the formula for the variance of x with respect to e of x. We generalize this to covariance of two variables using the new term covariance. And covariance is given by the product of the difference of x and y with respective expected value of x and expected value of y and averaged. This formula was formally introduced by Carl Pearson in 1896. Hence it is also called as Pearson covariance as well. The limitation of this covariance is that its value depends upon the value of x and y. So it is difficult for somebody to compare two different sets of association and comparing to what degree are they associated with their respective independent variables. So what we do is we standardize the covariance to create a -1 to +1 scale of association called correlation. The symbol for correlation is rho, and it is covariance divided by standard deviation of x, standard deviation of y. When x and y have a perfect correlation, covariance, it means for every value of x we can perfectly determine the value of y. It's a covariance of 1. And when it is negatively associated, it means when x increases, y falls, and to how much value it will fall by for every unit increase in x. If that is clearly identified, the covariance is -1. Let's look at some of the examples of covariances. Here we have a perfect association which we can define with the slope of this line. It is a negative perfect correlation. We see the next one, which is intermediate or medium strength correlation, and the third chart is that of completely random. There is no association. We cannot clearly determine y using x or determine x using y. In the next case, again the correlation is 0, because irrespective of what the value of x be, the y's value does not change at all. Essentially, the deviance or the variance in the values of y is 0, so there is no covariance. And when the incline of the line is less than 90 degrees with respect to x, or in this direction where x increases, y also increases, it's a positive correlation. And the extreme case of this is the +1 correlation. Now let's look at the explanatory part of the association of the two variables. So simple linear regression quantifies the relationship between x and y using the linear function y is equal to beta naught plus beta 1 x plus the error term epsilon. Now y represents the dependent variable, that is all the observed values of y. The beta naught and beta 1 are the regression coefficient of the linear function. This is what we determine when we try to fit a line through a data. And this we estimate using the data available to us, and we are estimating these for the population. So we determine the estimated beta naught and beta 1. X represents the independent variables, the observed values of x, and epsilons are the residuals. They are also called as error, and it is the difference or the leftover unexplained part of the regression model. So it is the difference between the actual value of y and the estimated value y hat. So this beta naught plus beta 1 x represents our y hat. Now these epsilons or the residuals are supposed to only carry the leftover noise or the randomness in the data, or rather than any signal or any intelligence or anything of value. So these are normally distributed with the expected value of 0. They have a constant variance. If it is not constant variance, and there are ways to treat the varying variances, and each of these errors or the epsilons for a given pair of x and y, or the difference between y and y hat, are independent of the errors in the associated with the other x and y's. So these are the properties of epsilons that we consider in our simple linear regression. Now we are only dealing with the sample data from the population for identifying or determining these relationships. So we don't get to know the beta naught, beta 1 and y at all. All that we get to know is the beta naught hat, beta 1 hat and the y hat, which are the point estimates of the populations beta naught, beta 1 and y. So since we have the point estimates and there is an element of uncertainty here, so we can compute the interval estimates using the central limit theorem. So we assume the normal distribution of each of these parameters and come up with the interval estimates. So each of the y hat is the conditional distribution of y given the value of x, and the y's for a given value of x are normally distributed with the point estimate being the y hat. So we will have for all x we will have different y hats. So using the normal distribution and the standard error associated with these y's, we determine the interval estimate. Let's look at a few examples of betas and rhos. We notice here that the beta in each of these three cases is same, but the rho is different. Similarly, here is a case of perfect rho. Here it is 1, here it is 0, here it is -1, and the error in the estimation of beta is also 0. So here we have we don't have any error at all. And similarly, we have this case where we have these negative betas here and different rhos. So once we have estimated our regression model, we have computed our correlation coefficient, we need to test whether the values observed from the data are just spurious non-zero values and the correlation is 0, or there is indeed an association between x and y. So we do the hypothesis testing using the null hypothesis rho equals to 0 and alternate hypothesis rho not equal to 0. From the sample data, the correlation that we compute is indicated by R, and we are trying to estimate the correlation coefficient for the population. So we use the test statistic, the t for n minus 2 degrees of freedom, because there are two variables here. So we'll be subtracting 2 here instead of 1 in the one variable case. And for a given level of alpha, since the alternate is not equal to, we will use the two-tailed test. And here is the t statistic formula that we use to compare with the theoretical t value for desired level of significance and n minus 2 degrees of freedom. This is done to ensure that the observed association is not a spurious non-zero association. If the confidence interval around rho equals to 0, around this r equals to 0 contains 0, it means the association is spurious. Similarly, we can do the hypothesis testing of the betas. Beta naught is the value of y for x equal to 0, and beta 1 is the rate of change of y per unit change in x. So here we again test for the hypothesis that the betas are actually 0 and what we are observing is just spurious non-zero values. So we perform the t-test to ensure that 0 is not contained in the confidence interval. If it contains the confidence interval of beta naught on beta 1 contains 0, it means the observed coefficient are spurious and there is no explanation of y provided by x. Now we don't do each of these manually. We use the software to perform these tests and we get the report, but we need to understand what these hypothesis tested actually means. So we use the t statistics, t distribution here to do the hypothesis testing of beta naught and beta 1. Finally, once we have looked at the reliability of the rho, the correlation, we have looked at the reliability of the coefficients. Now the y is an estimate which is a function of beta naught hat and beta 1 hat. So y hat is actually containing two estimated coefficients in its determination. In addition, we have the error term for the value of y. Now we determine the overall quality of the model by using the ratio of the variance explained as a proportion of the total variance in the values of y. So what it essentially means that when we did not have the intelligence embedded in x, our line was this blue colored line, a flat line where the expected value of y was y bar. By using the intelligence embedded in x, we have changed our estimate where the y is conditional on x. For different x we have different values of y. Now we want to check whether what percentage of the value of y is explained by this model with reference to the y bar. So if y is here, we know that originally it was y bar. Using the model we have been able to reach y hat, which is the value on the line. So the difference between the y bar and the y hat, or the variance captured between y bar and y hat, is called as the explained variance, and the total variance is the variance from y to y bar. So we take this variance divided by the total variance, which is our r square. So the difference between expected value of y and the expected value of y conditional on x is the explained variance. We used ANOVA to test the statistical significance of r square. That tells her how good our model is, or what percentage of variance in y can be explained using the intelligence embedded in x. Finally, we will also have the confidence interval around the y hat, which will capture the value of y. So the confidence interval of y is conditional on x. For different values of x, we have different values of the interval width. It is narrowest at x bar, y bar, and it asymptotically becomes wider as we move away from x bar, y bar. So here we see the confidence band of 95% for the values of y. So this gives us the estimated range within which we expect to see the values of y. So simple linear regression model is a series of estimates and a collection of hypothesis tests, which we typically do it using the software, and we don't advise you to do it manually unless you have interest in learning how it is done from first principles. A typical software report will give us the beta coefficients with their associated significance values. It will give us the standard error of y, based on which we can compute our y interval. Then we have the overall model's reliability using the ANOVA test, which tells us how good or bad the model is overall. Interestingly, you will find the significance level of beta 1 and the significance level of the F statistic in ANOVA for the regression model is same.